Okay, should we start? Okay, thanks everybody for being here. So I'm going to be giving my 2 cents worth. Basically, I'm going to be trying to throw in a few ideas about non-stationarity, and hopefully that's going to stimulate some interesting discussions later on. So basically, I'm going to be talking about non-stationarity in hydrology, what we've done so far, and hopefully where we would be going in the future, in the very near future. Okay, so let me start with this statement. I like this statement. It's from a document called Water Policy for the American People. It's from 1950. And what it says that however big floods get, there will always be a bigger one coming. So says one theory of extremes, and experience suggests it's true. And we tend to forget this. We tend to look at the observations and say we're observing larger values, and that's a proof of climate change. The number of times I heard people say, I've been living here for 50 years, I've never seen the water this high, or I've been living in this place for 40 years, I've never observed these temperatures. And that is not a proof of climate change. That's just a proof that the person is old and is still alive. Okay, that's all it says, actually. Because even in a stationary framework, the longer you're going to be observing a variable, the higher the probability that you're going to be observing large floods. The 100-year flood, you're going to be having twice as much probability to observe it if you have 40 years of data than if you have 20 years of data. So the longer you're going to wait, the higher the events you're going to be observing. And that doesn't mean there is climate change. That doesn't mean there is non-stationarity. I'm not saying that there is no non-stationarity. I'm not a denier of climate change. It's quite the opposite, actually. What I'm saying is that we have to maintain our scientific credibility. We hear so many people trying all the time to use all excuses to say this is a proof of climate change, and half of the arguments they're giving are wrong. Okay? And sometimes in life, the credit you try to get and you don't deserve ends up taking from you the credit you already earned. So we have to be extremely careful, I think, the way we talk about climate change and the arguments we present to justify that. This being said, there is climate change. There has always been climate change, actually. Never stopped occurring. And it will always be there. So we better learn how to integrate it in the way we model our variables and we design our structures and the way we manage them. Okay? That's what I'm going to be trying to speak about very quickly. So, first point I want to make is the amount of uncertainty that's associated to this. If we look at basically the outputs of different climate models into the future for the variable we know best, which is temperature, we're not even getting to precipitation. Different climate models, same scenario, we're observing really large difference in what they're predicting. You add to that the uncertainty about the scenario itself. What should we base our climate prediction on? And basically the uncertainty is so large that sometimes it's better to say, we don't know what's going on. Okay? And this is with the best variable we have, with temperature. So we see some kind of studies that try to present the future as a deterministic kind of scenario almost. And I believe we have to avoid that. We have always to insist on the uncertainty that's associated with everything that we're doing with non-stationarity. Let me show you this case very quickly. This is the stream flows at the Koulikoro station in the Niger River. And we don't have a pointer? Okay. So I think I'm loud. We've been observing since the early 1950s a decreasing trend that lasted for 40 years. 40 years of decreasing trend until the early 1990s, and it would have been very easy to say, this is climate change, this is the trend we're observing, we're going to be moving in this direction, stream flows will be negative in the future. Because if you keep extrapolating, that's what it means. Water will be going upstream, okay? Which doesn't make any sense. Of course, at a certain time, it bounces back. Would have been easy to do the same thing when we had a trend of 20 years, decreasing trend. It bounced back. We see quite a few studies in the literature that are just looking at trends that are observed over a certain period of time, 12 years, 15 years, extrapolating that into the future and doing non-stationarity, basically, and saying, here is my design of my structure, the 100-year quantile, that integrates the trend that we're observing. I don't believe that is necessarily the appropriate way to do things. And I'm going to be talking about this a little bit later. So the point I'm trying to make here is that we have to be careful about the way we introduce non-stationarity. We have to be careful about the uncertainty associated to that. And we have to be careful about extrapolating anything that seems present for a certain period of time. Okay? So how are we going to deal with it at the end of the day? Let's start from the start. Frequency analysis, we assume IID. We assume that our variable is independent, identically distributed, which basically means that we assume the criteria of independence, stationarity, and homogeneity of the data. We're going to be focusing on stationarity. Data suggests otherwise. Stationarity is not always valid, and we have to integrate that in our models. So that's how we started talking about doing frequency analysis in a non-stationary framework. And the obvious way to do it is to say, I'm going to integrate any trends or any information about dependence with any variables directly into the parameters of the model. I'm going to be focusing now on the annual maxima model, basically where we're taking the annual maximum value in our series. The same thing can be done by working on the peaks over threshold model. So instead of taking the annual maximum values, we would be taking all the values that exceed a certain threshold. And in statistics, we know that modeling the first with the GV, generalized screen value distribution, is equivalent to using the generalized Pareto distribution for the exceedances. So the idea, I'm not going to get into this now, but we could be working with the thresholds, with basically peaks over threshold, the exceedances above thresholds, and we would be adopting the GPD distribution, but there are also other things that are really interesting is to work on the inter-arrival time, basically the frequency of the extremes with the Poisson distribution, where we have the intensity parameter that can be modeled as a function of time or any other covariate. I'm just going to leave this aside. We're going to focus on the annual max. So, a distribution that has been used quite a bit to model annual maximum values, extreme values, is the GEV. It's a family that includes 3 distributions, very flexible, does a good job in hydroclimatology, and we've been adopting it. So we have 3 parameters, mu, alpha, kappa, which are the location, scale, and shape. So the first one is basically an indicator of the mean, the second one an indicator of the variance. And in a non-stationary framework, mu, alpha, and kappa would be function of some covariance. Time would be the obvious one, but we're going to see it's not necessarily the best one. And we can use as covariance any information related to some planet oscillation indices, but also land use characteristics, urbanization, any kind of changes that we can model. A number of models have been proposed. I would put them into 2 different groups. In the first one, the non-stationarity is basically focused on the mean. In the second one, the non-stationarity is focused on the mean and the variance. Very few try to focus only on the variance. Okay? So if I'm looking at non-stationarity in the mean, what I'm doing is that I'm putting my parameters of the model as function of some covariance. I would call the GV0 the stationary model, where the parameters are constant. Then I can go and look at the model where mu is a linear function of a certain covariate, which I'm going to call YT. Could be time, could be something else. We can look at models that are more complex, where mu, okay, the location parameter, is a quadratic function of a covariate. And basically, we can keep pushing this as far as we want. We can build models that are more complex. Obviously, the more complex the model, the more the number of parameters you're going to have to estimate, and you have to worry about parsimony. So you have to look at how much data you have and how to do this properly. We shouldn't keep adding the parameters just for the sake of doing it. Okay? I'm trying to move very quickly through things that everybody knows so that we can get into some interesting discussions. And I'm going to try to skip most of the equations because we don't have time for that. But, I mean, if there are questions, I have about 200 slides I'm not showing, so I can pull some of those to answer the questions and discuss things. So, 2 methods are obvious. Maximum likelihood method, which has always been used in this framework since the work of Coles. and then the generalized maximum likelihood method, which I'm going to be presenting very quickly. So the maximum likelihood method, we all know how it works. We build our likelihood function. We say that at the optimum, at the best estimates, the partial derivatives of that likelihood function over the parameters are equal to 0. I build a system which I'm going to solve. We usually work with the log likelihood function because it's easier. And when we build our system, we're going to be, if I assume the GV1 model where I have a linear trend as a function of my covariate, the explanatory variable, then I end up with 4 parameters in my GV model instead of 3 in the stationary case. I'm going to be building the 4 partial derivatives, and I have a system with 4 equations, 4 unknowns. I can solve it. Very simple. The maximum likelihood can be problematic. If you have a short series, we all know. If I'm working with distributions like the log Pearson type 3, I wouldn't even touch the maximum likelihood. I know the kind of problems it can lead to. Okay? But in general, we have problems with stability. We have problems when the size of the sample is small, and we need alternative methods. So what Sedinger and one of his students presented at a certain time is an extension of the maximum likelihood called the generalized maximum likelihood. And the idea is very simple. It's just to define a prior distribution on kappa, okay, on the shape parameter. And that makes things much easier. So for precipitation, they looked at the bounds and what can be used, and they defined a beta distribution. And basically, my precipitations will be bound between certain values, and we have an estimator of kappa, an expected value of minus 0.1, and standard deviation of 0.12. And the way we do it then is that we're simply going to be solving the same system we had with the maximum likelihood method, and we're adding to that system an additional constraint. And basically, we have the maximum likelihood system. We're adding a constraint that kappa is going to follow that beta distribution. That's all it is. And that's going to restrict the range. That's going to lead to much more stable solutions. With a maximum likelihood, to solve the problem, we need to use numeric methods. So we usually use methods like the Newton-Raphson approach. In the GML, we need something similar. We cannot integrate our basically do the integration in an analytical modes. Quite often, it's very complicated. That has been actually the main factor that slowed the development of Bayesian methods. Because for a long time, we didn't have the computing capacity. We could only solve academic problems in a Bayesian framework because we had to integrate things analytically. Now, we have the capacity to do this numerically. And the approach that we've been using is the Markov chain Monte Carlo methods, which will allow us to solve the problem, basically, of the integration. I'm not going to get into the details of whether we know the distribution or not, which method, the burnout period, and all that. But this method has been working very well for us, for hydrologists, and I don't see a reason to move away from this. We're going to be getting estimates of our parameters. What's of interest to us is the estimate of the quantiles. We have to review the notion of quantile, though, because we've always thought about the quantile as the value that on average over a very long period of time we're going to be observing every 50 years, okay, or every 100 years. In a non-stationary framework, basically the value is going to be changing with time if you have a trend, for instance. So if it corresponds to a 50-year quantile today, it may represent a 40-year quantile after a certain period, and it's just a 30-year quantile, okay? So we have to rethink the notion of quantile in a non-stationary framework. The value of the quantile now is conditional on a certain covariate. So if I write the equation of my quantile, in this case, we see that it's function of mu. And if mu is function of my covariate, time, or something else, then my quantile now is function of the non-exceedance probability, but also of the covariate. And this is a different way to think about risk, basically. The value of risk is changing with time. So a question that have been asked by people is, how am I going to handle this? If my risk is increasing, I'm designing a structure for the next 7 years, should I focus on the risk right now, or should I focus on the risk at the end of the lifetime of the structure, or should it some kind of average, some kind of integration of the overall risk throughout the whole period? And it's not an easy question. Ideally, you want to make sure that if you're saying this is a 100-year value, then for the worst case scenario, it is going to be the 100-year value. So if your floods are increasing, you're going to be focusing on the end of the lifetime of the structure. But that means we're over-designing at the beginning. So it brings all the questions about what risk should I adopt. Okay, I'm going to go through this. So basically this is the fact that for different models, the formulation of our quantile is going to be function of my covariates. So let's compare the maximum likelihood and the GML very quickly. By simulation, this is one case where we simulated different values of the shape parameter, different non-exceedance values, the value of P, and we compared the maximum likelihood and the GML as far as their bias and their RMSE. And we see clearly that for basically all values of the shape parameter, we're having a better performance with the GML. The bias is lower, it's positive, it's not negative, because we try to avoid negative bias in hydrology. We would rather overestimate than underestimate, basically. And the RMSE is systematically half, lower. So I'm convinced that we should be using approaches like the GML rather than something like the maximum likelihood. But there are problems with that. Let's look at a couple of case studies. Because one thing that we hear all the time is that non-stationary methods are still just for research, and they're not ready to be used in practice. In a lot of cases where we presented basically the proof that we should be using a non-stationary framework, the clients have been very reluctant. Some large companies, some big agencies have adopted these approaches. We've been working with them. But there is still a lot of resistance. So let me present very quickly a couple of cases to illustrate the importance of the method. So let's look at the annual max precipitation at the Rendsburg station in California. We have 51 years of data when we did the work, and this is what the series looks like. This is the type of series I can do a stationary frequency analysis with any time, and I'm protected, actually. I mean, I can go to any court of law with this one if I do a stationary analysis, and I'm fine, okay? It passes the stationarity test. So if I work in a stationary framework, we have the descriptive characteristics. I can go ahead and estimate the parameters of the GEV. We did it with the maximum likelihood over here, and we have the values in the bottom here. This is what the fitting is going to look like. We have our confidence intervals at the 95% level, and everything looks fine. However, let's try to dig a little bit deeper. If I represent here the annual max precipitation series with the series of the Southern Oscillation Index, what I see here is that whenever the value of the Southern Oscillation Index is low, I ended up with a year with extreme high precipitations. If the SOI is high, I have low precipitation, annual max precipitations. The year I had the lowest value of the SOI was the highest value in the whole record as far as the annual max precipitation. I have an interesting covariate here. I can basically model my annual max precipitation as function of the SOI. So this is a case where my covariate is not time, because I don't have a trend with time, but I have a form of non-stationarity, if you want, because I can now build my parameters as function of this index. That has a lot of interesting applications. For insurance, for instance, to look at their premium. Why should I give the same premium every year when in some years I know that the risk of getting flooded is much larger than in another year? I could be adapting my premium. So there are a lot of applications for this. Let's look at the way the annual max precipitation looks as far as the SOI, and the devil is in the details. So when I look at this, I see clearly that there is a relationship. But I don't know what form that relationship is. Is this linear? Is this quadratic? Is this basically a stationary model? I don't know which model works best. Now, we're hitting basically the first major problem with non-stationary models, is that before you start fitting and estimating the parameters, you have to know which model it is. Which kind of link do you have between the parameters and the covariance? So you have an additional step, and nobody wants an additional step. Makes things harder, because people want something automatic that they can run, and they have estimates of their parameters. So that's one of our focuses, to try to do that. So in this case, we're comparing the various models, the GV0, the stationary model, GV1, GV2, the quadratic model. The number of parameters depends on the model, and either one of these can work. Let's compare them. One way to compare models that are, one is a special case of the other, is through the divine statistic. I'm not going to go into the detail, basically, of this. And if we use the divine statistic, we realize that the GV1 model is a better fit than the GV0. Because you're comparing two models. One is more flexible than the other, but it has an extra parameter. So you have to integrate the parsimony into there. And then if I compare the GV2 with the GV1, I find out that the GV2 is a better model. So basically, the quadratic model is what I need to use in this case. And if I compare the results, this is where it gets interesting. If I look at the GV0, I'm looking here at the median estimator. With the stationary model, my median estimator is constant, no matter what the value of the SOI. We know that if SOI is low, we have much higher probabilities of getting extreme precipitations and floods. This is the confidence interval. And this is what we're trying to move away from. If I adopt the linear model, this is the way it's going to look, my median. And now we have something that's relatively, that integrates that information. This is the model that we have shown provides the best fit. And we see that basically the linear model value, even the upper bound, is not even within the confidence interval over here. Okay? The difference is really large. This is the model that we've shown it is the one that provides the best fit. This is probably the one that we should be using. And working with the stationary model over here would lead to systematic, considerable underestimation in low SOI years and systematic overestimation in high SOI years. It's worth it to do this. For a number of applications, we would be modeling the risk as a function of that covariate rather than assuming it's constant. It's interesting. So the problem, as I said, is that now I have two steps. I have to identify the best model, in this case the GV2, the quadratic model for the mean, and then do the estimation of the parameters. And people in practice are not happy about this. So we need to find a way to do both at the same time. And that's when we started looking at the birth-death MCMC approach. So this is an approach basically where, as we're running the Monte Carlo chain, we're changing the number of parameters. We're allowing the model to add or to kill parameters. And at the end of my chain, I'm going to be adopting the model where I stayed the longest. So this is what it would look like. So if I consider, now I'm already integrating non-stationarity in the mean and in the variance. So I'm adopting GV11 would be the stationary model with one parameter for alpha, one parameter for mu and alpha. And I can go to the GV12 where it's stationary in the mean, linear for the variance. Okay? And by adding, I have a birth of a parameter for alpha. If I have a death of a parameter for alpha, I go back to this. If I have a birth of a parameter with mu, with the mean, basically the location parameter, I end up with the GV2 one. So my model can keep having new parameters or killing the parameters when we realize that we don't need them. And we're going to see which model is actually the optimal one. So just an application to another station in California, Tehachapi station. This is what the data looks like. Manual max percip as function of the SOI. Same question, what relationship should I take? Is it quadratic? Is it which model? So if we look at the output for mu, for alpha, we see that we assumed stationary linear model, quadratic model. For alpha, this is the model where we're staying the longest. I'm not going to get into the mathematics. For alpha, the model where we're staying the longest is the stationary model. So the most probable model is the GV3-1 model. And we're speaking about a model that's quadratic for mu and constant stationary for alpha. Okay? What we're doing now is that we're doing the estimation of the parameters and the identification of the model at the same stage. So we're back to step 0. We're back to the position we had when we worked with stationary models, where I just take my data, run my procedure, I have estimates of the parameters. So there is no additional complexity in adopting a non-stationary model with this. So the output of the Monte Carlo chain, I'm going to skip through this. Let me give you a couple of applications, real-world applications on which we worked, and basically where this approach has been adopted. In Canada, this area here in the north is extremely rich in minerals. You need to transport large quantities of equipment up north to do the mining. That's a very expensive process, and even to feed the population that lives up there. So most of this is done by airplane, very costly. In the winter, all the lakes freeze, and we can drive straight through, basically, and take all the equipment. It's much cheaper. However, I need to know when is it safe to drive these humongous trucks on the lakes. So I need to know when it's completely frozen, when it's at least 40 centimeters thick. So I need a model to know what time is it going to freeze this year, and what time is the ice going to start breaking up, and I should stop doing that. This is really, I mean, if you haven't seen this, it's like a caravan, basically. It's straight line trucks, one after the other, for a period of around a month, non-stop, trying to move as much equipment as possible before the thawing, okay? So the question has been, how do I estimate the date it freezes up, and how do I estimate the date when I have to stop doing this? If you look at, this is a map for the breakup date, we see that breakup is occurring earlier in most of the stations. So basically lakes are freezing a little bit later, melting a little bit earlier, and the period where I can do this is shorter. I have to be very careful. And it's about now estimating for each lake, when can I start moving these trucks safely? We looked at the link with a very large number of climate oscillation indices, because in that area we're subject to a number of indices, the Arctic, the Atlantic, the North Atlantic, the Pacific. And the problem is not simple, because they all have an impact. And correlations come and go, because these indices don't have the same length period, basically, and they don't have the same impact. So in some years, their effect is going to add up, and you're going to observe good correlations, and then in some other years, they destroy each other, and there is no correlation. So correlation comes and goes. And the problem is highly nonlinear. So to show you one of the examples, this is Dead Man's Pond in the northwest, and we're looking at the date of freeze-up as function of the Pacific Decadal Oscillation Index. And we see clear link here. The higher the value of the PDO, the earlier the breakup is going to happen. So that's my predictor here. It's this climate index. The problem is that we have different climate indices with different relationships. So we need methods that can integrate a number of climate indices and have relationships that are more complicated than what I've been presenting, linear and quadratic. That's almost academic. It's very simple. Okay? So we ended up building a model. I'm going to show you the procedure we adopted for this. I believe I'm going to move here. What is supposed to be? Sorry. Okay. So another application, very quickly, to show you that this is already now at the stage where we can use this in practice. This is not just for research. This is modeling of the wind speed over the Gulf of St. Lawrence. There is a lot of interest in installing some wind farms in isolated areas because now it's costing a lot to connect them to the network or to generate electricity with fossil fuel, with diesel generators. And there are other problems. There is interest in looking at the erosion of the coastal line, at the stability of the structures around the coastal regions and all. So there was interest in looking at modeling the change in wind speed. And the way we proceeded is that we worked with reanalysis data where we calibrated basically our climate model to reproduce the past, and then once we're reproducing the past properly, we're generating the future. And what I'm presenting here is the changes in the 50% quantile wind speeds. And we see the areas with an increase in the wind speed and the areas with a decrease in the wind speed. And wind speed is not a simple variable. Because if I look at the 99% quantile, we see that the changes are much more significant, the increases and the decreases. However, I have information that I can use onshore and offshore, because there is interest also in this is basically the Hibernia area, so they're building offshore platforms here, and we were worried about the stability of those structures and the kind of winds they're going to be subject to and the waves that are generated and all. So this is a direct application where this approach has been used directly to model some structures, okay? And so we're looking at renewable energy, but more importantly in this case, we're really looking at marine structures and coastal erosion. Another application, completely different one, where we're adopting non-stationary models. Last one I'm going to be talking about very quickly, the Great Lakes system. The Great Lakes, we've been observing a decrease in the lake levels over the last 13, 14 years. Some houses that used to be directly on the lake are now about 100 meters from the lake. The impacts are huge, not just for recreation, for navigation. There is a lot of dredging going on in different areas. The impact is just humongous for a large number of activities. This is basically 20% of the world's fresh water in the Great Lakes. So just think about all the uses of this water for different applications. Different cities are drinking basically from the Great Lakes. And the question has been, is this going to continue? Is this a change that we're going to be observing? Is this a constant state, basically? Or is it a temporary state and we're going to be bouncing back? So the work dealt with this. And again, what we ended up looking at is the link with different climate oscillation indices. The problem is that we cannot work with the lake level because it's not a natural variable. It's not a random variable. It's a controlled variable. There is dredging, there are derivations, there are all kinds of things. So we have to work with natural variables, precipitation, runoff, evaporation, and rebuild the natural runoff and look at the lake levels with the controls that are existing. So the only way to do it is through the natural variables, what we call the NBS, the net basin supply components. So different methods were used. Using linear methods didn't work well. So we ended up trying different things. One method that ended up working well is using wavelet analysis, which is a linear method, by the way, but we transformed it. Wavelet analysis has been tried by a number of people to look at this problem. The problem is that it gives you qualitative assessment. For a certain period of time, we've observed a high signal of correlation between the lake area annual runoff and PDO, but it disappeared afterwards, okay? And how can we use this? The problem is that we're using these climate oscillation indices as if they are a sacred thing. This is an invention, a human invention. We're looking at the difference of pressure between 2 points, one in the southern Atlantic, one in the northern Atlantic, and we're looking at the difference of pressure at the surface of the ocean, basically. And we're saying this is a good predictor of the movement of the oceans, the mass of heat and all that. Part of that is a good predictor, but there is a lot of noise in that. And the idea is, let's try to extract the good signal from the climate oscillation indices to use it as a good predictor. So we used wavelet analysis to extract the good frequencies. What we do is that we do the wavelet analysis, we look at the thresholds above which we had a good coherence, we take those periods now, and we do an inverse wavelet analysis focusing on these frequencies that end up being good predictors. So we basically remove all the noise. And we create a modified oscillation index that is a good predictor for the variable I'm interested in, the lake area runoff, for instance. You see the idea? I'm not using the real original climate oscillation index. I'm using a modified one, which is a good predictor. I'm filtering the noise. The procedure ended up working perfectly. We ended up coming up for different seasons, for different lakes, for different variables, with the predictors and the models that explain what's going on. And we validated this historically to show that it represents a very good predictor. This is a very complex problem. But just by adopting a simple procedure, we can still use non-stationary models to understand what's going on and to model the future. Okay. So what we have said so far is that the relationship can be complex. I'm adopting naive models, linear quadratic models or log models, and the relationship should be much more complex than that. So one thing that we worked on with one of our students, Bushra Nasri, who's here with us, and I invite you to go see her poster. So I'm not going to talk much about this. I hope she's going to be explaining to you what she did. And what the idea is to use the B-spline model to model the link between the predictor, the SOI for instance, and the parameters of the model of interest. Okay? If I look back at the Ransberg, we realize that it's not just the SOI that's a good predictor of the annual mass precipitation, the PDO also is a good predictor. So we're looking for a model that can combine different predictors and that can give me nonlinear relationships of the parameters with those predictors. This can do it. So I really invite you to chat a little bit with Bushra. Then, the problem that we still have is that we're modeling things of the past. What I'm interested in is to understand how the future is going to be. I want to design for the future. And I said at the beginning that using a trend and extrapolating the trend is not a good idea. So how can I do that? If I have a link with the climate oscillation index, that's fine, but I don't know the value of the climate oscillation index in 3 years. I can use climate models to have some kind of extrapolations, but they're not that reliable. Actually, they're not reliable at all. Okay? So I need something a little bit better to build my predictors into the future so that I can apply these models in a predictive mode. Otherwise, all I'm doing is modeling the past. Do I make sense? And the idea here came up by using the empirical mode decomposition. I'm not going to, I know she's going to come kick me out of here very soon. So I'm going to go quickly through this. Okay? So the idea here, I'm going to skip the mathematics. The idea is equivalent of doing harmonics, but in a non-linear, non-stationary framework. It's an empirical procedure to decompose a signal and observation into a sum of IMFs, okay? A sum of signals that represent different frequencies. The same idea than doing harmonics. Okay? But this is non-linear, non-stationary. And as you go to higher level IMFs, you're going at the lower frequencies. So eventually, you can say this is a trend. But a trend really doesn't exist. A trend may be simply an oscillation that has a very long period. And when you focus on a certain window, all you see is a trend. But if you had a larger window, you may be observing a real oscillation. Okay? So by summing up these IMFs, I have the observed signal. The beauty of this is that these IMFs Once I build them, I can extrapolate them into the future. So by saying that this observed signal is the sum of these IMFs, I can go into the future now and say the future of my variable is simply the sum of the extrapolation of these IMFs. And I have a good predictor of the future, hopefully. So let's see how that predictor looks like. Showing you a case here of the global surface temperature anomalies, where we went, this is the real signal. We modeled with the EMD the signal up to 1973. And then from 1973, we extrapolated the sum of the IMFs. And this is what we obtained. We assumed we don't know the observed values. These are the observed values. And we see clearly that our model has predicted relatively well the increase and then the fact that the observed values will go through a sort of plateau. And by modeling the residuals with the K nearest neighbor model, we can build an interval around this to model the uncertainty around it. Another example, the Eastern Canada scaled mean winter precipitation. Same procedure. We went, assumed we only have data till 1990, built our IMFs, built our model with the EMD, said if we extrapolate this into the future, here is what we're going to be getting. We're not extrapolating the trend now, we're extrapolating the EMD, and this is what we obtain. Now, if we superpose this with the observed values, this is what we really observe. Again, we've been fairly successful in modeling this. But these are cases where I have a fairly long sequence. It's going to depend on the phase of the oscillations, basically. This ends up working fairly well. So if I had to bet on the future for the Eastern Canada precipitation, this is what I would bet on. So let's go back to our problem of the Randsburg station in California and the annual max precipitation. I'm almost done. Okay, a few more slides. So I'm looking here at the annual max precipitation as function of PDO, and I see a signal. And I'm saying now, we did a fairly good job in modeling the past, but what I'm interested in is knowing how the future is going to be so that I can design my structures. So let's apply this procedure to our predictors, to the PDO and the SOI, and let's see how they're going to be looking into the future. So we do the same thing, the historic forecast procedure, where we validate our model on observed values to see if they really perform well. And if we have good predictions, then we extrapolate it into the future. So we said we stopped in 1980. We stopped in 1980, built our IMFs, summed them up. In this case, we're summing up C3, C4, C5, the significant ones. We have our basically estimate of what the future should look like. Then we look at the real observations, which we didn't use to build this one. We're doing a fairly good job in modeling how things are going to be. And I can add basically the model of the residuals with the KNN approach, and I have an interval that includes fairly well the real observed values. Since this is working, I can go ahead now and apply it into the future. What's the PDO going to be looking like in the future by using this model? This is what I would bet on. And this now, we can feed it into the non-stationary GAV procedure. We can use it in non-stationary frequency analysis. Does it make sense, the idea? So basically, I have now a value of the predictor into the future. So if I do this, if I go and validate with the historic values, the values of precipitation, I have them only since 1950, but the PDO, I have them since the beginning of the century. So I can model my PDO fairly well, and I can validate that PDO model over the precipitation period to see how well it's working. And what I have here over this validation period, this is what I would have predicted as value of mu, the location parameter. This is the value of my quantile. And I predicted fairly well what was happening actually on the field, the observations. So if I wanted to build a prediction now into the future of my quantile, I'm not going to be just extrapolating this trend. I'm going to be using the PDO extrapolation as predictor in my GV model. And these are my estimates of the Q100 quantile, how it's going to be evolving into the future. We're getting closer to our objective. We can build predictions into the future of our covariates. We can build nonlinear relationships between the parameters and the quantiles, and we can use more than one predictor in the same model, assuming we have enough data to build all this. Okay? So this gives a small idea about some of the things that have been done. Things I didn't speak about, regional models, simply because the regional models that integrated non-stationarity are naive. One of the things that have been done, we did it in our team, and we assumed that the non-stationary signal is uniform over the whole region to do the estimation in ungauged basins. That's too simple, okay? Because in general, we do not have the same signal in all stations, at least the trends that don't have the same intensity. So ideally, we should be integrating the signal itself as one of the predictors. The same way we integrate the slope of the basin or the area of the basin as a predictor in the estimation in ungauged basins. Hasn't been done. It's very feasible. And I hope some of us will be working on that together. Let me show you a very small idea now. Everything that I've talked about so far is about the univariate case. All we're modeling is one variable, the annual max precipitation, the peak of the stream flow. But our hydrologic variables are represented by more than one characteristic. If I'm looking at flood, it's modeled by its peak, its duration, and its volume, three characteristics. So the multivariate framework has been developed, mainly using copulas, so that we're modeling not just what's happening with the peak, but the joint distribution of peak and duration, or peak and volume. And that's basically what things would look like. Now, we have the joint cumulative distribution function of these two variables. There's been a lot of work that has been done on multivariate modeling in a stationary framework. Nothing has been done in a non-stationary framework. So, a work that has been done by my colleague Fateh recently shows that the equivalent of a quantile in a multivariate framework is a whole curve. In a bivariate framework, a quantile is actually represented by a whole curve, the extremes of which are univariate quantiles, the quantile of the peak and the volume. And the real quantile that corresponds to a certain value of the risk is a whole curve. The higher the risk, the smaller the curve, until you get to some kind of probable maximum event, if you want. Okay? So this is in a stationary framework, but how is this quantile going to be evolving in a non-stationary framework? So everything we've been doing now, we have to do it in a bivariate framework or in a multivariate framework. And we started working on this. This is the case where we assume the non-stationarity only on the copula and the marginals. This is the case where we're assuming the stationarity on the copula. This is the case where we're assuming the marginality. This is on the marginals and this is on the copula. And the case where we assume stationarity on both copula and margins, we only have one curve, as I presented. So this is a direction that we're working on, developing the non-stationary framework for the multivariate case. Okay? There is a lot of potential over here, and I hope some of us will be working on this. There are a lot of things that need to be done. Integrating EMD in the regional model, doing the multivariate case with predictors like EMD, integrating B-splines, for instance, in the multivariate case. And this is just to build up on the things I presented now. But there are all kinds of other things that can be done. So there is a whole life of research for the young students that are here. Thank you very much.
Thank you very much. If you want to ask, you can have 5 minutes for asking questions.
My friend, please. I'm looking forward to your question. Yes. Understand it yet.
Okay. Thanks for the clarification, because the uncertainty is not defined in terms of comparing different models.
Absolutely.
It's defined in terms of comparing predictions with reality.
Absolutely.
And
I agree with you.
Perhaps all these models, as you said, are not reliable, so they cannot give even the uncertainty.
Absolutely. You see that in most of my work, I try to avoid using GCMs and climate prediction models.
I noticed.
I've been trying to stay away from that because it's so easy to get results. They look so good, but I have to do something I believe in, and I don't believe in those models, so I don't want to use them.
So it's not a matter of belief anyway. You compare and you see what happens in the past, and you compare as we do in hydrology.
They are not at the level of basically success that we can use them in practice.
Yeah.
It's not to say that they're not going to be there in the future. We need to keep investing on climate models, but I believe right now they are not at the level where we can use them in practice. I'd rather build a model based on observations, historic data, than try to do a climate prediction.
Okay, this was my first question. Can I?
Sure, go ahead.
1 second. So you correctly criticized the idea of projecting a trend. And you said it could lead also in negative flows or whatever. On the other hand, of course, you presented several methods. My comment is about only one. The linear trend in the mean. It's the same.
Absolutely.
Okay. So
Absolutely.
what's the meaning of doing this exercise with maximum likelihood or whatever if your assumption is something that you have already criticized?
I'm sure, Dimitri, you know the answer to your question. Okay, what we're doing is that we're building a linear model in the relationship between the parameter and a predictor. The predictor is not basically time. It's not something that's constant. So if I can build a good model for the predictor, then having a linear model is still going to lead me to some prediction that's not just a trend.
Linear in the mean.
Exactly. But that's why I criticized it. I said this is the first step so that we can obtain predictions into the future that are not simple trends, but we want to build non-linear relationships between the parameters and our predictors. That's why we moved into the B-splines. And we can move into harmonics. We can move into other things. So I completely agree with you, but Rome wasn't built in one day, or Athens if you want, okay? We have to build things step by step, and the first step is to avoid having basically a linear trend.
And tear some down.
Absolutely.
Yeah.
Do you have any questions?
No.
Okay. Thanks, Dimitris. Thank you. Any other questions? Yes.
Well, starting from the beginning, when you see the normal regression, is that the case which you discussed for trend in the mean value for normal distribution. So the next step, it was just we changed the normal distribution for any other forms. We use over 10 distributions in Gam's pocket. In R written, you can find over 50 distribution. So my question, GIF was applied by Coates and other 10 years ago, but only as an example. Well, what we think that despite of the fact that the time series doesn't fit the GIF distribution, if it would be very long, it would fit GIF distribution. It is why we, so like that the warming of climate is manifested by cooling of the climate, something like this. So my question, is whether you fall in love to GIF once forever? Thank you.
No. I'm
one more thing. What was the best trend in our Polish data? It was the constant CV, the trend in the mean and the trend in variance, but with keeping constant CV because of the doctrine of parsimony in numbers of parameters. Absolutely. In maximum likelihood. we can very often fall in getting the result in maximum likelihood.
Absolutely. I think I mentioned briefly the parsimony problem. You're raising a very good point. The GV. I tried to focus on this presentation on the annual max model, no POT, and on the GV distribution. We've been building the non-stationary model for other distributions. This last example I presented, basically we're modeling Q with a log normal 2-1 model. So it's a log normal, non-stationary log normal model that's stationary for the variance, non-stationary for the mean, and the volume with an LN2 model that's, this is actually linear, the variance, quadratic of the mean, and this is a stationary model. So just by accident, in this example, you see that the marginals were represented by a log normal model. We've been working with a bunch of distributions, the Gumbel, the log Pearson type 3, normal, log normal. There are a whole bunch of distributions for which the non-stationary model has been developed, the maximum likelihood and the Bayesian estimator, and I believe there is still an effort to be done on this. There are some distributions for which nobody has started working on building non-stationary models. We need to do it. I try to focus on the ideas, so I focused on one distribution, but I'm absolutely in agreement with you. We need to be doing this for a whole bunch of distributions, and I'm not in love with the GV. It's a useful tool. It's wrong, like all tools. But it's been doing some job for us. We'll keep using it until we can do better. Okay?
Do you have a question? First of all, congratulations. The talk was really exciting. And I have, first of all, a very brief comment and then a question. The comment is, I think in your second slide, you mentioned that the stationary analysis is based on the assumption of independence, usually. And I don't think this is really correct. We have many instruments, many tools for taking a correlation into account. So I think this should be made clear. And then my question. And you talked also about the test for stationarity. And here my question comes, because I'm curious how you decide that it's worth taking non-stationarity into account. Because as Professor Stropczewski mentioned, I'm really amazed on your capability to reconstruct for the future the climatic indexes, but I think that when you take non-stationarity into account, and therefore dependence from an external variable, you increase uncertainty. So actually, how can you judge whether it's convenient in practice for engineering purposes, for instance, to take into account non-stationarity or not? Because if you assume stationarity, of course, you get a more robust estimate. So how can you decide?
Thank you very much. Two excellent questions. Let me start by what was the first question?
Correlation in stationary analysis.
Yeah. So how do I decide that there is a non-stationarity, and how do I decide how to integrate it? I love the Bayesian framework. I agree with the point you made about the independence. If you look at the Mann-Kendall test, for instance, there is a modified version of the Mann-Kendall test that takes into consideration the autocorrelation in the series, which reduces the effective size of the sample. It's a useful tool. I'm more in favor of using Bayesian models. Okay, so we developed, for instance, a Bayesian procedure for the detection of change points. With any test, hypothesis test, you're making assumptions. You're looking for something for a given date. Is there a shift at this specific date? You're making a whole bunch of assumptions, which are usually not valid. I've always kind of disliked the modified Mann-Kendall process test, for instance, because you're assuming that there is autocorrelation in the sequence, and you're modeling that and the impact of that autocorrelation on the trend detection, but the autocorrelation is not that independent from the non-stationarity, but you're still assuming stationarity. So you're modeling the dependence of the sequence while assuming, in a certain sense, stationarity, but, I mean, there is a link between them. I like to go to the Bayesian framework, where I think I'm integrating all the information, and I'm looking at the whole sequence. I'm not looking for a signal for basically the mean of the sequence. I can, in the Bayesian procedure, I can identify an upward trend and then a downward trend and then an upward one, and I can model different sequences within my series. That's the tool we've been using. Is it perfect? Absolutely not. It's more powerful than hypothesis testing, I believe. Okay? Now, the comparison of stationary and non-stationary models. I'm not saying that we should throw away stationary models. Everything we've built and we're trusting, we're standing under these buildings, we're trusting them that they're not going to fall on our heads. Everything we've been doing is based on stationarity. Stationarity has been good to us. Okay? We did some good things. I don't think we need to throw it away. What I'm saying is that we need to do the non-stationary model also, and we need to compare. I presented a couple of cases where we compared with the divine statistic, the stationary and various non-stationary models. In the decision making, I'm not going to automatically adopt a non-stationary framework. If nothing else, because politicians are not used to it yet. It's not going to get the full support. So my idea is we have to do the stationary and the non-stationary model. That's going to give us a better representation of the risk. The same way we're using univariate and multivariate models, and that's going to give us a better representation of the risk. Statistics is a science of ignorance. When you do statistics, by definition, you're ignorant. If you were not ignorant, you wouldn't be doing statistics. You'd be using deterministic models. And we tend to forget that. Statistics is about modeling our level of ignorance, in a certain sense. And we tend to forget that. Yes, but then we build models that look good mathematically, and then we fall in love with them, and we trust them. And we know they're wrong. So the idea is, let's keep a whole bunch of wrongs, and by combining them, hopefully I'll have something that's almost right.
Okay.
That's the way I look at it. Did I answer your question?
Yes.
Thanks.
There could be room for more discussion.
Oh yeah, I hope we're going to have more discussions, yes. There is another question here, I'm sorry.
More question.
Okay. In non-stationary case, we used to refer the probability of accidents to the whole lifetime of the structure. Yes, and it was possible to derive also, to estimate confidence intervals and so on. Everything was okay. But if you look in the reality, you should then define that your bridge would last, for instance, for 50 years. Your dam it means extrapolation for 1,000 years or something like this, which looks, of course, quite unrealistic. Apart of the fact that your trend, decreasing trend can give you the negative variance or negative mean or something like this, and it is really a bit difficult to explain designer that such things can exist, that there would be no river at all after, say, 500 of years. Thank you.
Yeah, I absolutely agree with you. And I mentioned that doing an extrapolation of a trend is wrong. It's simply wrong. And it's going to lead to some really serious problems, because we give a false sense of security to people that we're integrating non-stationarity when we're not doing it properly. We're not even trying to do an effort on doing it properly. So I absolutely agree with you on this point. That's not the way to do it. And most of my presentation has been on trying to show how we could avoid doing this in that manner by integrating additional information. So I'm definitely in agreement with you.
Thank you very much. And I invite Taha to present the remaining multivariate frequency analysis using the function. Thank you very much.